Welcome back to our lecture on linear system theory. This second chapter is about vectors and matrices. In a large part, it reviews basic facts from linear algebra that should be known to you from your undergraduate math courses. We will move fairly quickly over the background material and indicate what is assumed to be prior knowledge. If you do not feel familiar with any of the material that's assumed as prior knowledge, I urge you to look it up in your undergraduate course materials or any relevant textbooks. You can also find lots of material on the internet, and there are excellent videos explaining basic concepts of linear algebra on YouTube. If you're unable to find any suitable material for a particular topic, please feel free to contact me and I will provide you with some relevant references. Now let's start with something that we all know even from high school math, namely vectors in 2 dimensions, so in a plane, or in 3 dimensions in a space, and concepts that are related to such vectors. For instance, the length of a vector, the angle between 2 vectors, vector addition and subtraction, dot products, cross products, and change of coordinate systems. What linear algebra, as you know it from your undergraduate math, really does is it generalizes these notions to real and complex vector spaces of higher dimensions, so more than 3, and, as we shall see in this course, even abstract vector spaces. And we'll learn in just a few lectures what exactly is meant by this. But let's first review real and complex vector spaces of higher dimensions, meaning dimensions higher than 3. Rn is defined as the set of all n×1 column vectors of real numbers, where now n can be larger than 3. And we write this as x in Rn, which is the same as saying that x consists of n scalars, which are stacked up in a vector, and these scalars are obviously real numbers. Throughout the course, when we have a column vector that's called x, we indicate its kth entry by writing xk. So whenever we have a vector x defined, then xk automatically refers to its kth entry. Analogously, a real vector space of dimension n can be extended to a complex vector space of dimension n, which we write as Cn, and it's simply defined as the set of all column vectors with n complex elements. So now these entries of the vector are now not real numbers, but they are complex numbers. It is assumed that you have come across complex numbers during your undergraduate math courses. You may wonder, however, why we're dealing with complex numbers now in the context of linear algebra. And the reason is very simple. Basically, almost every result that we will derive in this course equally holds for real and complex vectors. And it's not much harder to state the proofs for complex vectors, and since they represent the more general case, there's no reason not to do it. In other words, when doing all the work for developing the theory in this course, we basically get the complex case for free, and therefore we'll rather deal with the more general complex case, and then the real case will just be a special case of the complex case. Next, in undergraduate linear algebra, we have not just been dealing with vectors, but also with matrices. We will write the set of all m×n real matrices as R to the m×n. Similar to a vector, a matrix can be written in terms of its scalar elements. So if A is in Rm by n, A consists of a bunch of scalars which are ordered in such a rectangular form, where we have m elements in a column of A and n elements in a row of A. And we'll write these elements by A11, A21, A12, and so on. So Aik, which are real numbers for all I in 1 to m and k in 1 to n. Here's also an important remark about notation. Throughout the course, we will denote matrices by uppercase letters, and we denote its elements by lowercase letters because they are scalars. And we will also use the corresponding lowercase letter of the matrix letter. So if the matrix is an uppercase A, we will use a lowercase a to denote its elements, and then use the indices ik to mean the element in the ith row and kth column. And we'll do that automatically. So whenever we have a matrix A defined, we'll automatically use aik to denote its elements. Again, analogously to the vectors, we will use Cm by n to denote the set of all complex m by n matrices, which look exactly like the real matrices, only that now the scalar entries of the matrix are complex numbers instead of real numbers. It is assumed that you are familiar with how to do matrix multiplications. So for example, if you have a matrix, here a 3 by 3 complex matrix, and a vector, here a 3 vector, then the multiplication of A with X looks like this. And it is expected that you know all the rules for calculating the result. In particular, the result will be another 3 vector, and this 3 vector can be expressed as this combination of the columns of A that is shown here. So we multiply the first column with the first entry of the vector x, the second column with the second entry of x, and the third column with the third entry of x, which we can write in a more compact way by this sum over all entries xk of the vector and these column vectors of A. More generally, you should be able to carry out a matrix-matrix multiplication, so where A is a general m by n matrix and B is a general n by p matrix. Then we can form the product AB, which we call C here, and it's another matrix of the type m by p. So the first dimension of A and the second dimension of B, and actually these two dimensions, so the second dimension of A and the first dimension of B, they have to match, otherwise the multiplication AB is not properly defined. And then the entries of the result C, Cij, are defined by this sum for all I from 1 to m and j from 1 to p. And again here, the remark that for a matrix multiplication to work, the according sizes have to match. So the second dimension of A has to be equal to the first dimension of B. And this is actually a fairly important remark for the entire course, because it serves as a good check that the formulas that you have derived are actually correct. Because if the corresponding sizes do not match, then you know that at some point you've made a mistake in your derivation. Another very important remark is that matrix multiplications in general do not commute. So this is a mistake that's very frequently being made, even in the exams, that for two matrices A and B, in general, AB is not equal to BA. Let's look at two quick examples to make sure that we have fully grasped this fact. In the first example, we let A be equal to the column vector 1, 2, which is nothing but a special case of a matrix where we just have one column. And we let B be this row vector of the numbers 1, 2, 3. Since A is in C 2 by 1 and B is in C 1 by 3, the two dimensions here match, and hence the product AB exists, and it can be calculated as follows. We can put A and B into a little diagram that I like to use to multiply two matrices, and we put A here and B here in order to calculate AB down here, and that's the result that we get for the product AB. Again, it's assumed that you know the rules for calculating this product. Now, if we flip the order of these two matrices and try to multiply B with A, we realize that the second dimension of B does not match the first dimension of C, and hence the multiplication of B with A is not possible, and hence the product BA does not exist. In our second example, we let C be the 3 by 1 matrix defined like this, and D be the 1 by 3 matrix defined like this. Now, looking again at the dimensions, we see that the second dimension of C matches with the first dimension of D, and hence the product CD exists. And by using our matrix multiplication scheme, we obtain that the product CD is given by this 3 by 3 matrix that contains all ones. If we again try to flip the order and multiply D with C, we realize that in this case, the second dimension of D matches with the first dimension of C, and so the product DC exists, and by our standard multiplication scheme, for the product we do get this result, which is just a 1 by 1 matrix or a scalar of the value 3. As one can clearly see, the result for CD, which was a 3 by 3 matrix of all ones, and the result for DC, which is just a scalar of the value 3, are very different results. Let's quickly summarize our conclusions from these examples. So if A and B are two matrices whose dimensions are such that the product AB exists, then in general, AB is not equal to BA because, first, BA may not even exist, as in our first example, or second, BA may exist, but may have different dimensions and be therefore something totally different from AB. And third, even if the dimensions of BA match those of AB, the entries of BA may be different from those of AB. Often, it is useful to partition matrices into blocks. For example, we could partition this 4 by 5 matrix into 4 blocks as shown by these lines. Then we name the 4 resulting blocks similar as if they were elements of the matrix A, only now they are matrices, so we use capital letters. And then we name the block in the first row and the first column A11, the block in the first row and second column A12, the block in the second row and the first column A21, and finally the block in the second row and the second column A22. Multiplying block partitioned matrices works in the same way as the normal matrix multiplication. So for example, if we have two matrices A and B that we want to multiply, and A is split into 4 blocks and B is split into 4 blocks, then the result AB is again a partitioned matrix where each of these elements is given by the same formula that you would apply if all of these entries here were scalars. When we look at this more closely, we see that there are a bunch of matrix-matrix products in this formula. And of course, all of them have to exist So A and B have to be partitioned what we call conformably, meaning such that all of these single matrix products that we have in the formula have to exist in terms of the corresponding dimensions. Here, a few final remarks about matrix dimensions. Matrix dimensions are critically important when calculating with matrices. As it was mentioned before, it is often a good idea to analyze the meaning or correctness of a given statement by first checking the relevant dimensions. Because if the dimensions in the statement don't match, then certainly the statement cannot be true. And this is often a really good check. Second, to make statements in this course more transparent, the dimensions of the matrices involved are often not stated explicitly. Since all the statements made in this course are correct, you can always assume that the dimensions have to be such that the statements are possible. On the other hand, if there's no statement made about the dimensions, you can choose any dimensions you like as long as they are compatible with the statement and the statement will remain true. So you can always assume that the matrices involved in the statement have the appropriate dimensions for the results to be sensible. And then finally, as we have seen, dimensions depend on the order of matrices in an expression. So for example, if you have two matrices, A in C1 by n and B in Cn by 1, then AB will be a scalar, whereas BA will be an n by n matrix. So keep that in mind, that the outcome in terms of dimensions depends on the order in which we multiply matrices. A very common application of matrices and vectors that you have seen in your undergraduate linear algebra course are linear equation systems. So matrices can basically be used to write a collection of m linear equations in n unknowns in a compact form by just writing a times x equal to b, where a in Cm by n is called the coefficient matrix, b in Cm is called the right-hand side, and x here in Cn is the vector of unknowns that we want to solve the linear equation system for. So for example, if we have these four equations for the three unknowns, x1, x2, and x3, we can write this equivalently in this matrix vector representation, where we summarize all of the coefficients of these equations in a big matrix A. Then we have the vector of unknowns, x1, x2, and x3. And finally, we have the values on the right-hand side of the equation system stacked up in the vector B. For such a linear equation system, we have the fundamental fact that we call fact 2(1). Namely, there exist exactly three possibilities for the solution of such an equation system ax equal to b. The first possibility A is that there is no solution for x in Cn. And that's also called that the system is overdetermined. The second case B is that there are multiple solutions for x in Cn, and that's called that the system is underdetermined. And finally C, which is usually the case that one is looking for, but it's not always true, is that there is exactly one unique solution for x in Cn. And again, you have probably seen the statement of this fact in terms of real numbers. So where A is a real matrix, B is a real vector, and the vector of unknowns, C, is also a real vector. However, the very same fact for the real case carries over one-to-one to the complex case. Next, let's define the concept of the transpose of a matrix and the adjoint of a matrix. First, the transpose is defined for a real matrix. So if A is an m by n matrix, then its transpose is an n by m matrix, and it's written as A with a little t in the exponent, and it's simply defined as the matrix whose rows are the columns of A, and correspondingly whose columns are the rows of A. So we just flip the matrix. Now, we could also define the transpose of a complex matrix. However, this is not what generalizes our theory to the complex case. If we want to generalize our theory to the complex case, then we have to generalize the transpose to what's called an adjoint matrix. And the adjoint of a complex m by n matrix is not just the matrix A transposed, but in addition, we have to take the complex conjugate of all of the entries of A. For this, remember that the complex conjugate of a complex number, so for instance x plus jy, is equal to x minus jy. So we have to flip the sign of the complex part of the number. In this course, we will use a star in the exponent to denote the adjoint of a matrix A, and to reiterate, this stands for the matrix that we get if we first of all transpose A, and then also we take the complex conjugate of all of the entries of A. One thing to realize here straight away is that if A is a real matrix, then taking the transpose is actually the same thing as taking the adjoint. Because if all of the entries of A are real, then taking their complex conjugate doesn't do anything and will give you the very same elements, and hence taking the adjoint is the same as taking the transpose. And again, since we will be dealing with the way more general complex case for most of this course, we will be dealing with adjoints much more than with transposes, but you know that if you switch to the real case, then adjoint is exactly the same thing as taking the transpose. Some essential properties of the adjoint are summarized in fact 2.4, which we will not prove. For any complex matrices A and B, we have the following properties. First, if we take the adjoint of the adjoint, we will get our matrix back. Second, if we take the adjoint of a sum of two matrices A and B, then this is nothing but the sum of the two adjoints. And third, if we take the adjoint of a product of two matrices, then we get also the product of the adjoints, but with the order reversed. So first we were multiplying A and B and take the adjoint, and now we have to multiply the adjoint of B with the adjoint of A. With regard to the remark that we have made before, in this fact there is no statement about the dimensions of A and B. However, we clearly cannot multiply matrices of arbitrary dimensions, and we can also only add matrices of the same dimensions. So how you should read this fact is that these statements hold for any matrices A and B, which only have to be such that the sum or the product exists, but otherwise they're totally arbitrary. All of you have probably seen the concepts of an identity matrix and a zero matrix. The identity matrix, or simply called the identity, is a square matrix whose elements are all ones on its diagonal and all other elements are 0. So this is what the identity matrix looks like, and we use the letter capital I to denote this identity. Sometimes we will also write I with an index n instead of I to mean explicitly the identity in C n by n. So when the dimension becomes important, then sometimes we use this notation instead of just writing I. And if we just write I, we mean identity of the appropriate dimension. It is easy to verify, and that's the main property of the identity, that if we multiply the identity matrix with another matrix, either from the left or from the right, then we will always get our original matrix A back. And that holds for any matrix A. The zero matrix that we write with a simple 0 is any matrix whose entries are all 0. And by any matrix, we mean that the zero matrix is not necessarily square, but it can be of arbitrary dimensions. And if these dimensions are important, we sometimes also write the 0 with an index m by n instead of just the 0 to mean explicitly the zero matrix of dimensions m by n. It is very easy to verify for yourself that if we multiply any matrix A with the zero matrix from the left or from the right, then we will always get a zero matrix, and that holds for any matrix A. Now let's define the concept of a left and a right inverse. So if we have any matrix A, then a left inverse of A is another matrix B that has the property that if I multiply A from the left with B, then I get the identity matrix. And similarly, a right inverse of A is another matrix C, such that if I multiply A from the right with C, I also get the identity matrix. Two important remarks about left and right inverses. First, note that they do not require for A to be square. And second, they are not necessarily unique, meaning that the matrix B is called A left inverse if it satisfies this equation, and the matrix C is called A right inverse if it satisfies this equation. Now we have the following proposition to 6. If a matrix has a left and a right inverse, then first of all, the left and the right inverses are equal, and second, A must be a square matrix. So let's prove this proposition. By assumption, A has a left inverse, so there exists a matrix B such that B times A equals to identity. And moreover, by assumption, A has a right inverse, so there exists a matrix C such that A times C equals to the identity. So this is what's given, and what needs to be shown in the first part A is that B equals to C. We start with the given fact that AC equals to identity, and now we multiply both sides of the equation from the left with the matrix B. And now we apply the given fact that BA equals to the identity matrix, and also we use the property of the identity that states that BI is equal to the matrix B. So what we're left with is identity times C equals to B. And again, we use the property of the identity that identity times C is the matrix C. And so we get exactly what we wanted to show, namely that C equals to B. In the second part B, we still need to prove that A is square. We start by assuming that A is an m by n matrix, where m is not necessarily equal to n. Since the matrix product BA exists by assumption, because we have BA equals to identity, the matrix B has to be of the dimensions P times M, where P is any number. And moreover, we know that the product of BA is in CP times N, and by assumption BA equals to identity, where the identity is a square matrix, And therefore, we must have that P equal to n, and so B is an n by m matrix. Now we can make a similar argument for the matrix C. First of all, since AC exists, C must be an n by q matrix. And then since AC is an m by q matrix, and AC equals to identity where the identity is squared, we have that Q must be equal to M, so the matrix C is an M by N matrix. Finally, in part A, we have shown that B is equal to C, so in particular, the dimensions of B and C have to be equal, and this automatically means that M must be equal to N, and hence A has to be square. Some remarks about proposition 2.6. Not every square matrix has a left and a right inverse. However, if a square matrix has a left inverse, then it also has a right inverse, and vice versa. So if a square matrix has a right inverse, then it also has a left inverse. And in this case, both of them are identical by virtue of proposition 2.6. And because of that proposition, it makes sense to state the following definition, definition 2.7. Let A be a square matrix. The inverse of A is a unique matrix that we denote A with a -1 in the exponent that satisfies that A times A inverse equals to the identity. If a square matrix has such an inverse matrix, then we will call it invertible. Otherwise, we will call it singular. A few important properties of inverses are stated in fact 2.8, which we will also not prove. So for two matrices A and B, A times A inverse equals to A inverse times A equals to identity. So if a matrix has an inverse, we don't just have A times A inverse equal identity, but we also have it the other way around, A inverse times A equals to identity. The second property, if we take the inverse of the adjoint of a matrix, this is the same as taking the inverse of the matrix and then taking the adjoint. And if we take the inverse of a product of two matrices, then this is the product of the inverses, except that the order is reversed. So same as for the adjoint, we get here that AB inverse equals to B inverse times A inverse. Next, we have the definition of the determinant of a matrix that you have certainly seen in your undergraduate linear algebra course. The determinant is defined only for square matrices, so that's important. So if you have a square matrix, you can compute its determinant, and it's a scalar value that is denoted in two ways in this course. First, determinant of A, like this, or simply A with two vertical lines. It is also assumed that you are familiar with minors of a matrix. To remind you, the ij minor of a square matrix is the determinant of the n-1 by n-1 matrix that remains if row I and column j are removed from A and multiplied with the factor -1 to the I plus j. So, for example, assume that we want to calculate the ij minor of the matrix A, which looks like this in terms of its elements. Then the first thing we need to do is we need to cross out the column that corresponds to the element Aij and also the row that corresponds to the element Aij. What we get from this is an n-1 by n-1 matrix that's indicated in blue here, And in a second step, we have to take the determinant of this matrix, and in a third step, multiply it with the factor -1 to the I plus j. So this factor is either +1 or -1, depending on whether I plus j is even or odd. Again, it's assumed that you are familiar with minors and how to compute determinants, and also the geometric interpretation of determinants, which is nothing but a scaling factor for volumes that are mapped by the matrix A, where the sign of the determinant of A signifies whether the linear mapping preserves or reverses the coordinate orientation. So also don't be confused by the two vertical lines for the determinant. It doesn't mean the absolute value, but it stands for the determinant of A, which can be negative. Let's quickly review a few rules for calculating determinants. And we start with the formula for the determinant of a 2x2 matrix that everybody knows. So the determinant of the matrix ABCD equals to AD minus BC. For any square matrix in Cn by n, where n is greater than or equal to 3, the determinant can be calculated recursively by applying what's called the minor expansion formula. In fact, the minor expansion formula has two variants. The first variant is to expand how it's called by a row of A. And for this, we first have to pick an arbitrary row I of the matrix A. And then we can write the determinant of A as the sum over all elements in the row I of A multiplied with the corresponding IK minor. The second variant is to expand how it's called by a column of A. To this end, pick an arbitrary column K of the matrix A, and then the determinant of A can be written as the sum over all rows, I equal from 1 to n, over all elements of the column K times the corresponding minor MIK. So in both of these formulas, MIK denotes the IK minor of the matrix A. Let's make a quick example for a general 3x3 matrix as stated here. In order to compute its determinant, we can, for instance, expand by the first row of the matrix, and we obtain this expression, which corresponds to the sum over all elements of the first row multiplied with the respective minor. Clearly, these minors are determinants of a corresponding 2x2 submatrix of the original matrix. And since we know how to calculate determinants of 2x2 matrices, we can use this expansion formula to calculate the determinant of a 3x3 matrix. Alternatively, we could also expand by any of the columns of the matrix, like for instance in this case by the third column. And what we get is the elements of the third column multiplied with their corresponding minors, which can then again be calculated as before in order to obtain the determinant of the 3x3 matrix. What we can see from this is that by using the minor expansion formula, determinants of arbitrarily large n by n matrices can be calculated recursively, because by expanding the determinant by a row or a column of A, we reduce it to the sum of n determinants, where each of the determinants is now just an n-1 by n-1 determinant. And so we can go on like this until we have a bunch of 2 by 2 determinants for which we have a formula to calculate them. Some important properties of determinants are summarized in fact 210, which we will not prove. For any two matrices A and B, which are square and of the same dimensions, and any scalar lambda in C, we have the following properties. First, the determinant of the transpose of a matrix equals to the determinant of the matrix, and that in fact also holds for complex matrices. So that's one of the few situations where we also consider the transpose of a complex matrix. B, if we take the adjoint of a complex matrix and take the determinant, then what we get is almost the determinant of A, but we also have to take the complex conjugate of that number. If we take the determinant of the inverse of a matrix A, we get 1 over the determinant of A. D, if we multiply a matrix A with the scalar lambda, then the determinant of that product is equal to lambda to the n times the determinant of A, where n, remember, is the dimension of the square matrix, and E, the determinant of the product of two matrices A and B, is equal to the determinant of the product BA, and this in turn is equal to the determinant of A times the determinant of B. Remember that AB doesn't have to be equal to BA, but according to this statement, the determinant of AB is always equal to the determinant of BA. In definition 2.11, we define the cofactor matrix of an n by n matrix A, which is another n by n matrix whose elements Cik are given by the Ik minors of A. Then the adjugate matrix of A is the transpose of the cofactor matrix. So we just take adjugate of A, that's what we use for the notation of the adjugate matrix of A, and this is just the transpose of the cofactor matrix C. It's important not to confuse the adjugate with the adjoint matrix, and we have the following properties for adjugate matrices. So if A and B are two square matrices, then first the adjugate of the adjoint of A is equal to the adjoint of the adjugate. Then B, the adjugate of A inverse equals to the inverse of the adjugate. And C, the adjugate of the product AB equals to the product of the adjugates, only that we have to reverse the order. So adjugate of AB is equal to adjugate of B times adjugate of A. And finally, one of the key reasons why we're dealing with adjugate matrices is because they allow us to explicitly compute the inverse of a matrix. And that's stated in fact 213. So a square matrix A in C n by n is invertible if and only if its determinant is non-zero. And if that's the case, the inverse of A can be computed explicitly as follows. A inverse equals to 1 over the determinant of A, and this exists because the determinant is non-zero, times the adjugate matrix of A. Proposition 214 provides a bunch of useful formulas for computing the determinants of block partitioned matrices. In the first statement, we have that X and Z are square, and then the determinant of this matrix, where we have a 0 down here, is equal to the product of the determinant of X and the determinant of Z. Similarly, in B, we have that x and z are square, but now we have the 0 up here, and we have the same statement. The determinant of this matrix equals to the product of the determinant of x times the determinant of z. In case C, we have that A and B are square, and A is invertible, and then we have that the determinant of this matrix, A, B, C, D, equals to the determinant of D minus CA inverse B times the determinant of A. And again, similarly, in the case D, we have that A and D are square and D is invertible. And then the determinant of the matrix ABCD equals to the determinant of A minus B times D inverse C times the determinant of D. Now, for the proof of proposition 214, in the case A, note that the matrix X, Y, 0, Z can be written as the product of these two matrices, where I denotes the identity. You can easily verify this formula for yourself by just multiplying the two matrices on the right-hand side using the rules for matrix multiplication for block partitioned matrices. By fact 210, it follows that the determinant of a product of two matrices is equal to the product of the determinants, and hence the determinant of this matrix is equal to the product of these two determinants. Now, let's first take a closer look at this second determinant. We realize that down here in the last block, we have an identity matrix, which means that it's only ones on the diagonal and zeros everywhere else. So we can use the minor expansion formula repeatedly on the columns of this last block in order to see that the determinant of this matrix must be equal to the determinant of x, because then on each column of this last block we only have one single entry with a 1, and so all of this collapses until we get down to the determinant of x. For this first determinant, we can do exactly the same thing, only that we expand by the first block columns. And what we get if we do this is that the determinant of this matrix equals to the determinant of z. You can verify for yourself that if you repeatedly expand by the columns of the identity matrix here, all expressions that contain elements of this Y matrix entirely drop out because they get multiplied by zeros. Parts B and C are actually left as a homework, as they are part of exercise sheet 1. For part B, you should find a factorization very similar to the factorization that we have used for part A. And finally, part D is very similar to part C, and so we have concluded the proof of proposition 216. Now we define the concept of a Schur complement that we will encounter again later on in this course. Observe that in the case of proposition 214c, we have stated a matrix that looks like this. So D minus C times A inverse times B. And that's actually called the Schur complement of A in this block partitioned matrix. Similarly, in proposition 214d, we have stated a matrix that looked like A minus B D inverse C. And that also has a name, and that name is the Schur complement of the matrix D. Now, there's another proposition 215 for this block partitioned matrix ABCD, and it reads as follows. Let A and D be square if A is invertible and A and B commute, or if D is invertible and C and D commute, then we have the following identity, namely the determinant of this block partitioned matrix equals to the determinant of AD minus BC. We notice that this formula very much looks like the determinant of a simple 2x2 matrix. And in fact, this formula can also be applied to block partitioned matrices, but only under these given assumptions. And finally, we have a very useful theorem stated by Sylvester, namely where A is an m by n matrix and B is an n by m matrix, then the determinant of I plus AB equals to the determinant of I plus BA. And by this little index, you can notice that actually the dimensions of this matrix are different from the dimensions of this matrix, but nonetheless, their determinants are equal. So let's also prove this theorem by Sylvester. And for the proof, consider the matrix stated here. You should quickly verify for yourself that this block partitioned matrix has consistent dimensions with the m by m identity in the upper left-hand corner and the n by n identity in the lower right-hand corner, and the matrices minus A and B in the corresponding diagonal blocks. It's immediately clear that the identities Im and In are square and invertible because the inverses are just, again, the identity matrices. So the requirements of proposition 214c and 214d are met, and we can use them to calculate the determinant of M in two different ways. First, by proposition 214c, the determinant of M equals to the determinant of this expression times the determinant of Im. It's easy to see that the inverse of Im has to be Im itself, because Im times Im is again identity. And second, we can see that the determinant of Im equals to 1 by just using the minor expansion formula. So the whole expression simplifies to the determinant of In plus Ba. Second, by proposition 214d, we can write the determinant of M as the determinant of this matrix times the determinant of In. By the same arguments as above, the inverse of In is In itself, and the determinant of In equals to 1. So what we get here is that determinant M is equal to the determinant of Im plus AB. And if we look at these two results, we now have the determinant of M is equal to this expression and the determinant of M is equal to this expression. So these two expressions must be equal and our proof is complete. Our final new concept in this chapter is called the trace of a matrix. And the trace of a matrix is defined only for square matrices, and it's given simply as the sum of all diagonal elements of A. So we write trace of A equal to the sum from I equal 1 to n of the diagonal elements AII. Now, at a first glance, it seems a little bit random to define the trace of a matrix like this, and it's not clear why this should be of any importance in any types of calculations. However, the trace of a matrix turns out to be more important than one would think at the first sight, and we will come across the trace more often in the later part of this course. For now, here are a few important facts about the trace. For any two matrices A and B, which have to be appropriately sized. First, the trace of a plus b is equal to the trace of a plus the trace of b. Second, the trace of the product of AB is equal to the trace of the product of BA, even if A and B are not square. And third, the trace of A star A, so the adjoint of A multiplied with A, equals to the sum of the absolute values of all elements of A squared. Finally, we review a few properties of matrices when they are viewed as maps. These properties should also be known from your undergraduate linear algebra course. In fact, matrix multiplication can and should be viewed as a particular instance of a function or a map. So a matrix A in Rm by n assigns to any vector in Rn another vector Ax in Rm. So here's the connection between matrices and functions that we have both discussed before. In fact, there exist all the parallels between them in terms of inverses, injectivity, surjectivity, and so on. In fact, an inverse of a matrix can act as an inverse function that reassigns x to the image Ax. So matrix multiplication is nothing but a special case of a function, and this special case is called a linear map. In this expression linear map, let's first look at the expression of a map. So definition 223 states that if x and y are finite dimensional real or complex spaces, such as Rn or Cn, then a function between them, so a function that maps from x to y, is also called a map. Second, let's look at what it means for such a map to be linear. Definition 224 assumes such a map F, which maps between two complex spaces, or analogously, it could also map between two real spaces. Then this map F is called linear if for every two vectors x1 and x2 in the domain of this map and every scalar lambda, we have the following two properties. A, f of x1 plus x2 is equal to f of x1 plus f of x2, and B, f of lambda times x1 equals to lambda times f of x1. In the rest of this chapter, we will just look at the different effects that one can cause with such a linear map. And for a start, in our first example, we look at the mapping effects of a diagonal matrix, in particular the matrix A that's shown here. So it's a 2 by 2 real matrix, and correspondingly the map of A is one that maps two-dimensional vectors into a two-dimensional space. Note that we cannot draw the graph of this map. That's because the graph lives in the product space of the codomain and the domain, and this product space would obviously be R4, and we can only draw up to 3 dimensions, so it's not possible to represent the graph of this map visually. Instead, we visualize its effect by looking at what the map does to particular vectors, and we start with the vector b1. And since the vector b1 equals to 1, 0, it gets mapped by the matrix A to the vector 3, 0. Similarly, we can map the vector b2, which equals to 1, 0, to the vector ab2, which is the vector 0, 2. And if we do the same thing to a vector drawn in blue here, we get this red vector. And if we do this for all the vectors on the unit circle shown in blue here, we get this red ellipse where the length of this axis here is 3 and the length of this axis is 2. So essentially all values in the x1 direction get dilated by a factor of 3 and all values in the x2 direction get dilated by a factor of 2. The second example of effects that can be caused by a linear map is a rotation, and for this we choose a rotation matrix that you have probably seen in your undergraduate linear algebra course. The rotation matrix that we call B here is defined by this expression for any arbitrary angle phi in R. For example, for phi equal to pi third, we obtain for B this matrix, and we can look at the effect that this matrix has again on the vectors B1 and B2. Unsurprisingly, the matrix B rotates both vectors in the counterclockwise direction by the angle phi, so this vector here is equal to BB1 and this vector here is equal to BB2. And similarly, all other vectors on the unit circle just get rotated by the angle pi over 3 in the counterclockwise direction. The third effect that can be caused by a linear map is flipping. And to this end, we have defined a flipping matrix C, which looks like this. So let's see what it does to our vectors B1 and B2. And what we get here is this vector for CB1 and this vector for CB2. And one could think that this is a rotation by 90 degrees, but notice that B2 gets rotated by 90 degrees in the counterclockwise direction and B1 by 90 degrees in the clockwise direction. So C cannot really represent a rotation, but instead it's a flipping of vectors by the diagonal of the second and fourth quadrant. And here's the corresponding remark that the flipping inverts the order of the two vectors B1 and B2 in terms of the angle that they have with one of the axes. Note that this cannot be replicated by any rotation, so flipping is really something different from a rotation. To summarize, matrix multiplication is a linear map between two vector spaces. We will prove later on that in fact any linear map between vector spaces, even of higher dimensions, so Rn and Rm or Cn and Cm, can always be represented by a real or complex matrix. So the set of linear maps and the set of matrices is identical. Then we have seen by 3 examples, so without a proof, that a linear map between two spaces Rn and Rm is a combination of 3 basic effects. Namely, the first one is a dilation, meaning a stretching or shortening of a vector depending on its direction. A rotation, preserving the orientation of the basis vectors. And a flipping, which actually inverts the orientation of the basis vectors. These effects can be combined by multiplying matrices of different types. So for instance, in our case, multiplying the dilation matrix A with the rotation matrix B is a combination of rotation and dilation, and multiplying B and C is a combination of flipping and rotation, and so on. In the next few chapters, we will actually leave this arena of geometric interpretation as we generalize the theory to more abstract vector spaces. Nonetheless, it's always good and helpful to have these basic geometric interpretations on your mind.